So let me say, our next speaker is Jörg Schmiedmayer, and he's a professor at the Technical University of Vienna in Austria, and he has done a lot of work, umpteen amount of work on co-atoms, and he has received many awards. I can mention a few, but he certainly has received. He's a full member of the Austrian Academy of Sciences, fellow of the American Physical Society, Austrian Physical Society, and so forth. And I thought I saw, the medalist. Yeah. Yes, he's received the Victor Hess Prize of Austrian Physical Society, and the Wittgenstein Prize, which is, if you know Wittgenstein. Right. So with that, today, Jörg is going to give us a talk about what atomtronics experiment teaches us about many body physics. Yes, and what this means for integrated metal wave circuits. Jörg, the floor is yours.
Yeah, thanks a lot for organizing all the conference and giving me the opportunity to talk a little bit about our work on atomtronics, or we rarely call it atomtronics, we call it integrated metal wave optics for a long time, and if the word becomes to be atomtronics, and we can use that too. So it's one of the things that kept me awake for the last 30 years, this integrated metal wave optics. And I will give you a few of the insights that we came up with from doing experiments with these integrated metal wave devices, and how I think that it might be very interesting how the field can develop and do things like that. I mean, in the beginning, I would say there was this vision that you combine the two worlds, and I still remember exactly how this thing came about. And when I did hydrogen physics and nuclear physics for my PhD, but I was very much interested in all these metal wave experiments that Helmut Rauch did, and and we had all these discussions about GHZ and Bell's inequalities and all these things that are in Helmut Rauch and Anton Zeiling's group when I was a student in Vienna. And then I was thinking out, then I got some money to go to some conferences after my PhD, and I went to a mesoscopic physics conference, where there was Landauer and Büttinger and Imri and Moti Heilblum and all the others. And it fascinated me, this way of making electron optics and defining electrons in nanostructures that had the size of their wavelengths. And then I went out to do a postdoc up at Harvard, and one of the first talks I heard was from Bill Phillips on laser cooling, and I had no idea about laser cooling because we had nothing heard about laser cooling in Vienna before. And it was, for me, it was striking that basically if you just put in numbers, that the structures you can make in nanofabrication and the structures and the Bohr wavelengths you get from laser cooling matched exactly what we had in the quantum electronics devices that I heard from Moti Heilblum and the others in the thing. So the question was, I was fascinated by the way of, can we make microscopic devices where we combine nanofabrication with atom optics to really build atomic devices? And out of that, partly came the atom chip and all the things that we did. So the basic idea was, can we do for atomic physics, things like we did for electronics and optics, take this metal wave interferometer, which I was working on at that time in Dave Pritchard's lab, and put it on a chip and make it robust in the same way as electronics becomes robust or optics becomes robust. And for that, of course, you first had to think about which interactions to use. And we basically set out to use the magnetic and electric interactions and not so much the optical dipole interactions that is now used for many of the beautiful experiments we heard in this type of thing. So maybe I just remind you that, for the magnetic potentials and electric potentials, you always have to think about, how big of the fields you need to really make really strong confinements. And you find very typically that, a microkelvin is 67, 67, Gauss and microgauss. And so you basically, if you can get very small, very small temperatures, like microkelvin temperatures, you only need a few Gauss to trap atoms, and you need only a few volts to trap atoms very close to an electric structure. So both of those things basically add up to make them extremely very easy to, if you can make them small, you can make them part. And then one of the key insights came from some old papers that I had known from Helmut Rauch's lectures about neutron physics and about, Mariana transition and spins, which was the way, basically the ideas of how we then really made these microscopic traps goes back to an idea that was published by Frisch and Segre in 1932 to study Mariana transitions, because they wanted to make a minimum of the field, a very well controlled minimum of the field, to look at spin transitions in an atomic beam. And what they did is they took a wire and an homogeneous field and said that, if you take a wire and an homogeneous field, you basically subtract these two fields and you get a very well controlled minimum here. And what is really nice is that the gradient, so the confinement, depends on 1 over the current. And then suddenly you can make extremely strong confinement for atoms that are magnetically trapped by making very small currents. And that's exactly the thing that you need for making these very small traps. And you can make them in wire configurations, make traps, and the rest, I think, is history. The first idea of doing this, in fact, is an old paper from Vladimirsky, who thought about doing this for neutrons in 1961 in the Soviet Union. Yeah, and the first experiment, basically, of showing that these things is true was something that I presented at IQEC in '92, which is about 30 years ago, where I showed that really you can trap and guide atoms with these type of potentials. So, and then there was lots of things to play around with these. Of course, in the end, you're going to have to build chips. And for that, to make this, the long story short, there was again a funny story that the first time I talked about chips was on the Max Planck Institute of Solid State Physics in Stuttgart. And when I said what currents I need, current densities I need, 3 people jumped up and said, this is impossible because, and they presented 15 review letters, because electromigration kills thin wires that have this type of currents. And I was lucky that I didn't read these papers, but I just went into the lab to a friend of mine, which was Charlie Unterreiner at that time. I was a young scientist in Vienna, and we tried to blow up wires. And in fact, we had wires that were used for quantum electronics on semiconductor substrates, and we couldn't blow them up. They had enormous current densities, and then we said, okay, let's do exactly that for making this type of chips. And that's why we used then gallium arsenide or silicon substrates with gold wires and high quality evaporated gold wires. And it turns out that you can send up 10 to the 8 amps per cubic centimeter to one or two of these wires. And you can put electric potentials where you have 100 volts over microns on fields. And that has to do because, you have this beautiful and extremely well-controlled way of nanofabrication of metal layers on semiconductor substrates. And that made it much, much easier to make these types of chips, which were then later on, really developed also with the help of Ron Follman and Donatella Cassetari. She was one of my first students in working on these type of chips. With the guys at the Weizmann Institute to really develop this type of chips. Now you can basically play around with that. You can load atoms in these things. You can load them in 1 micron size wires, and you can make a Bose-Einstein condensate out of that. And there are beautiful experiments, and there are, one has to mention also, of course, Ted Hensch and Jakob Reichel, who did, fantastic things, and it was always a fun to have a good competition with the Hensch group. So now, if you have a wire, if you have a current that goes through a metal wire, it doesn't always flow straight. And if it doesn't always flow straight, it creates magnetic field inhomogeneities, and you can use these atoms to measure them. And in fact, one of the first applications we did, with these type of things, and those are the first patents we got on that, was for a magnetic field sensor. And it turns out that it had a fantastic field sensitivity of about 4 nanotesla, and we could measure magnetic field changes of 10 to minus 6, an order of 10 to minus 6. And that was extremely small things that we could measure, and so that there was a beautiful way of looking at current flow. And by the way, this is now was now then later on perfected by Ben Lev's lab in Stanford, and it's now really tool to probe current flow and magnetism in solid state types of systems. And there's this beautiful experiment that he did in the last few years using this type of experiments. Now, if you want to go on, and if you want to go and do experiments with the coherence, you need to split and to look at interference. And for that, the question was, how can you split a magnetic trap? Now, there Maxwell's equations play you a trick, because you find very easily that corrugations are exponentially suppressed with the distance from the source in Maxwell's equations. So you either have to have extremely good control about the system to be able to make very small changes in the potential to split, say, a single trap into 2, or you have to go to some trick. And the trick is basically to couple to the topology. All these fields that we create are the basic principle, the basic building structure is a quadrupole. And the quadrupole has a singularity in the center, and the magnetic field makes a rotation around it, and it's basically a pole. Now, if you find something that couples to the direction of the magnetic field, then you can make structures at arbitrary distance from your sources, because that would couple to the topology of the field and not to the field itself. And that was something that you could go back and look at again in an old neutron experiment from Dieter Dubers and others, where they looked at dressed neutrons and did it for a completely different way. And they had done the calculation completely correctly, which was later on forgotten, because most of the time people looked at dress states of magnetic fields only in the scalar part and forget the vector component. But if you take the vector component into account, you couple to the topology, and you're allowed to make really the coupling you can create double wells in an extremely robust way. And that allowed us to coherently split a trap into 2 and get these beautiful interference fringes and make a coherent set of manipulations on that part. That sets you up, so to speak, to look at coherence and interference on this type of experiments. So what do we have? The atom chip is an integrated circuit. We can make atomic ensembles very deep in the one-dimensional regime. We can cool regular, standard makes it cool to about 0.1 on h bar omega r, which is a transverse trapping frequency, and we can cool to about 0.2 times the interaction energy. And we can, experiment with a few hundred atoms to a few 10,000 atoms in these extremely elongated traps, which have an aspect ratio of 1 to 1,000 or 1 to 10,000, something like that. And then there's all these tools that we have, like we have a control of the longitudinal potential we show you by using digital mirror devices. We can make this robust splitting. We have a detector where we can, by using fluorescence, detect every single atom. So we basically have 100 percent detection efficiency of every single atom. And we can do correlation analysis and interference analysis. So there was a question, how small of a systems you can work with on these chips. In our latest experiments on this parametric meta wave amplifier and making correlated pairs, we had an average of 2 to 3 atoms in each pulse. And even for these only having 2 to 3 atoms in this pulse, we could measure more than 10 dB number squeezing, so more than a factor of 10 number squeezing in the system. So you can do experiments with very, very small systems if you detect every atom, and you can do that basically by fluorescent imaging. Now, we do all our experiments with one-dimensional systems, and we'll see very soon why we think that's important. And if you do it with one-dimensional systems, you would have what does it mean one-dimensional? It means that both the transverse directions are completely frozen out. It means that the interaction energy and the temperature is much smaller than the transverse trapping frequency. And then if you are in a regime of where we do most of our experiments now, in the so-called quasi-condensate regime, you can describe your as you will see later on now, your system with an order parameter that has fluctuations and they have density fluctuations and phase fluctuations, and these are thermally populated. And these phase fluctuations will then be exactly the thing that we can probe with interference experiments. And it's also beautiful because this type of models are they're based on exactly solvable linear model, which in the low energy effective field theory description can be a bosonic latential liquid. Its excitations are sound waves, has a linear dispersion relation, so it basically can model two relativistic conformal quantum field theories. And that was beautifully, exemplified by, all the work by John Cargy and Calabrese and others. Now, what's interesting, what I will come back to that also, is that if you take two of those systems and you couple them together, you get a non-trivial quantum field theory, which is the Stein-Gordon model, and which is in a very general way. Now, let me see, now we can look at coherence of these integrated meta-wave circuits, and what does them, and we see that the many-body evolution, there's some very interesting many-body evolution that's triggered by the quantum noise of the beam splitter. So what do we have? If I take a beam splitter, if I take a single harmonic trap and I split it, what do I get? I get that the even states are mapped to the symmetric states and the odd states are mapped to the antisymmetric states. Yeah. And during that splitting process, I have a tunnel coupling and because these are atoms and they're interacting with each other, I have some kind of charging energy and nonlinearity in there. Now, if I do my system in one dimension and one-dimensional systems, what does it mean? It means that I'm only sitting in the ground state here, and the first excited state is not populated. So the first excited state is populated with vacuum. What does the beam splitter then do? The beam splitter then makes these two states degenerate, and the symmetric state is connected to the original trapped state, and the antisymmetric state is connected to the vacuum state. Now, you know what happens in a regular beam splitting quantum optics. This vacuum state gets populated by the quantum noise of the splitting. Yeah. And so you have a short noise in the splitting, which enters in the antisymmetric state of the double well. And this short noise, this quantum short noise, is directly accessible in the interference experiments. And the other thing that I have is that this quantum short noise in the splitting adds energy to the system and starts a many-body evolution, which we will look into the part. So basically what we do is take a single system, we split it into two, and if the coherent splitting is perfect, as good as quantum mechanics allows you, the order parameter, the phase of the order parameter will be an exact copy, but I will have number fluctuations left and right. And so I can take the symmetric state, and we'll find that the symmetric state is connected to will contain all the thermal populations of the initial state that I had. And the antisymmetric state will contain only the populations that comes from the quantum mechanical splitting process. Yeah. Now, this is a very strongly non-equilibrium state because there's a thermal population and there's a population coming from the quantum noise. And in many of the experiments, this population will be much smaller than that population. And now if I have a completely isolated system, I can ask the question if these two states will thermalize. If the population will become thermal or will not become thermal, and what will happen in there. Yeah. And we can measure the thermal state by creating two independent condensates and looking at the interferences. And you see that if a coherent is split, you have an extremely narrow phase distribution. If you create them independently, you have a completely flat phase distribution. Now, to make a long story short, that's now, summarize of about, 5 years of work. So we do the experiment. It's basically you take that, you make an interference experiment. Yeah, you take a single slice out of this interference experiment and measure the phase. So in this interference experiment, you can see about, this typical signal to noise in this data. That's an experiment with about 1,000 atoms. Yeah, that's a total about 1,000 atoms in there. So, but it's a standard, standard absorption imaging when you think about, what type of, it's nothing fancy with a lens or something. It's just a good camera and right adjusted light intensity and diffraction limited optics. So what do you see? You can very nicely characterize that by the mean square contrast of the interference pattern. And you sum that, interference pattern summed over the whole length of the system. And what you see is a very rapid decrease, a slow, some kind of a plateau, and a very slow further decrease. Yeah. And so what you find out is that this very rapid decrease is some kind of a light cone-like evolution of decoherence. So you basically have an exponentially decaying correlation function emerge in a light cone-like thing. So basically, if you sit on the system, you see a horizon that expands throughout the system. Outside, you have long-range order. Inside, you have a thermal state. This thermal state can be interpreted as a pre-thermalized state, which was predicted in high energy physics. So you have basically so what we said, we had the light cone like evolution, emergence of a pre-thermalized state, which is characterized by a general statistical ensemble, which was predicted by Srednitsky in the 50s, and later on and rediscovered by Olshani and Marcus Rigol and others in the form of the non-equilibrium physics. And so you have this you can basically create a generalized Gibbs ensemble where we can basically measure the occupation numbers. And you see that, it's typical of this ensemble, 0.5 would be the quantum noise. And if you do some certain type of splitting, you create very strongly non-classical phonon states and very, states where there's many, higher phonon occupation numbers. And then we basically, looking at it later, you find a further decay, which looks like a nonlinear relaxation model. And then if you really design your trap in the correct way, you can get an inverse light cone and basically get all the coherences back. So you basically what you see is in between there, you have a system that looks like a classical statistical ensemble, and then quantum mechanics comes back, another classical statistical ensemble, and quantum mechanics comes back. And these are recurrences in that part, from about the system of 10,000 atoms in this type of part. So first of all, what have we learned is that the splitting, if you make a superposition, and I think that's true for any superposition that you make, and that will be also true for Donatella's superposition of the two vortex states or something like that, you will get the quantum noise of during the time you make the superposition from the beam splitting will introduce introduce an energy and we'll start a non-equilibrium evolution. Now you can go and use optimum control to reduce this type of things. And we thought about that a lot. And we did, making fancy splitting ramps. You can basically, get something like, you can either do it adiabatic, but that takes very long time, or you can do optimum control and you can speed it up by something like 2 orders of magnitude, the splitting. And that looks promising. And we have seen some of that where we can basically measure both the population imbalance left and right and the relative phase left and right. And we found that we can reduce the population imbalance by about 7 dB, and have basically perfect contrast. And if you look at the uncertainty product and take away the photon shot noise from the detection, you basically are in an Heisenberg limited way that the delta n times delta phi is 1 for a system of about 1,000 atoms. And overall, in this experiment, something like 150 atoms entangled in that pi. So in principle, you can do that, but nevertheless, there's still always some kind of a quantum noise left over in a system. Now, what does it tell us? It tells us the observation that we have is that the physics is dominated by the quantum excitations in the system. And the natural way to describe such a many-body systems is through the excitations in an emerging effective model, and that's usually quantum field theory. So let's in the future think about the quantum gas in an atomtronic devices at temperature T equals 0 is a vacuum state. And the excitations are like particles that propagate in the vacuum. Energy density is like geometry, and you can go on and define analogs for that. Why do we have these emergent models? Because the complexity of the many-body wave function does not allow to observe all the details. We can only measure few-body observables, and this leads to a coarse graining, and automatically within a renormalization group framework leads to these effective quantum field theory descriptions of the many-body system. And I think these experiments tell you that it may be very useful for atomtronics devices to look at the system, to really do not the experiment with the atoms, but to the experiment with the quantum excitations of the system, and they being the ones they are the ones that carry information, that carry all the other things in the system. To show you more about that, would allow you one of the other models that we can realize on there, which is the Cyborg model, by coupling to tunnel coupled superfluids. If you take a tunnel coupled superfluid, you get a very complicated Hamiltonian, and it was shown by Gritsev, Polkovnikov, and Demler in 2007. Using density phase approximation, neglecting everything higher than second order, that this very complicated microscopic Hamiltonian can be mapped to something that's called the quantum Cyborg model, which is a lattice liquid plus a non-trivial term of the field phi, where the field enters in a cosine of the phi, cosine phi. And phi is nothing else like the phase difference between the left and the right system, as you basically have now a quantum field living in a cosine type of potential. And what is nice is that in the experiment, these parameters, we have very good access to these parameters with a phase or a spin healing length and the phase coherence length. And the system can be characterized by the ratio between the spin healing length and the phase coherence length is ratio Q. Now, why is this Cyborg model interesting? Because it can be mapped at many, many different physical models. It was, in fact, the first model in high energy physics where the particles had mass. It's basically equivalent to the Theorem model, which was shown by Sidney Coleman. It's equivalent to the Coulomb gas model. It's equivalent to XY models. It's equivalent to extended Hubbard models and half-inch spin chains. And recently it was shown that it's extended to string breaking, confinement, and entanglement in expanding quantum fields from high energy physics. And so it's a very, very broad model that covers, if you talk to people from solid state physics like Terry Jamarki, he thinks that the Cyborg model is much more powerful than the Hubbard model, even in solid state devices. Now, how can we probe that this is really the quantum field description? We usually do that with correlation functions. And what do correlation functions are? The correlation functions are basically correlation functions of some observable, some operator O, and this operator O basically, characterizes some degree of freedom. The measurement operator is freedom, and this correlation function can usually be decomposed in a disconnected part and a connected part, whereas the disconnected part basically is uninteresting because it's fully determined by all lower order correlation functions, and the connected part is basically the one that has new information about the system. So if I have no connected parts higher than second order, then I have a Gaussian model. So if somebody tells you that he does experiment with a strongly correlated system and can't show you higher order connected parts, you can tell him, okay, if your experiment is not sensitive enough to measure higher order connected parts in correlations, I can describe your experiment with a Gaussian model and you don't see anything about the strong correlations. But what does it mean? What are the connected parts? So the fourth order connected part is basically to two-body interactions. The sixth order connected part is related to three-body interactions. These are genuine three-body interactions. They cannot be decomposed into two-body interactions. And the eighth order connected part is basically genuine four-body interactions that cannot be decomposed in two-body and three-body interactions. So you have, looking at correlation functions, you have a beautiful tool to look at the complexity of your quantum field that you have in your device. Now you can do that, and we measure that, and we basically can, you see that if you are in a system which should be separable, then you see that the connected part of the fourth order correlation function is 0. If you're in a system which only lives, so basically this is a system where this cosine potential is completely irrelevant, it's too small. Then down there is a system where this cosine potential is extremely large, and you only see the quadratic part of that, and you also have again a Gaussian theory, and in between, when you see the complete potential of the cosine, you have a non-trivial quantum field theory where you have strong correlations and you see the interactions, and you can play that around, and it turns out that you can calculate what you would expect for these higher order correlation functions and the connected correlators, and what you measure. And it turns out for the fourth order correlator, for the sixth order, eighth order, 10th order correlator, the system, what we measure is perfectly in alignment with the Saint-Gordon model. And we're limited to the 10th order correlator, not by the quality of the data, but by the complexity to calculate connected correlation functions. Yeah, to calculate the connected correlators. Yeah, we could probably go to much higher orders, but even for the 10th order correlation function, we had to throw away most of our data. Otherwise, we would have not been able to calculate it. Therefore, the error bars are much larger. But it's nice to see that for us it was very surprising that even though the derivation of the Saint-Gordon model from the two-tunnel coupled superfluids included very strong approximations, basically threw everything away than second order, that up to 10th order correlator, that basically means up to genuine 5-body interactions. Yeah, the system we build in the lab is described by the quantum Saint-Gordon model. And what's also beautiful, you can see, this model has topological excitations. You can see them directly in interference experiments, and you can play around with this, and you can, if you fast cool, you can trap the system in different vacuum states, and this would be related to something like silicon as false vacuum states up here. Now, we also showed that how out of these extremely strongly correlated states, classical statistical physics emerges again. And of course, if you design it in the right way, these correlations would come back. The quantum correlations come back, and we showed them for the fourth and for the sixth order correlation functions. One of the examples that I think which would be really cool, where we can use the physics of the excitations in these atomtronic devices, to build really cool things. And I would like to how to build a quantum field machine. So it's basically playing with it, doing physics with the excitations in the quantum field that we have on our device. Yeah. So we want to build machines and study processes where the number of particles on one hand is large. So quantum mechanics is essential to understand and describe its dynamics. And so it's basically, we can use many-body quantum systems that are described by these quantum field theories. And why is that interesting? Because there's an interface between statistical mechanics and quantum physics. We can probe the role of information in quantum thermodynamical process. Role of information means that what do I know of the system and what do I don't know of the system, which is related to what is work and what is heat. And it allows it, I think it allows it to build machines that cannot be calculated efficiently with classical computers, especially if we build this type of machines using an extremely strongly correlated quantum Gordon model, then we can basically have a chance maybe to calculate the equilibrium properties. We cannot calculate non-equilibrium properties for now. So that may be. So what's the idea behind that? It's basically is that to use that as I said before, to use the system of atoms there as where the temperature T equals 0 state would be the vacuum, and basically experiment with the excitations on that system. Yeah. And so if you take an elongated 1D system, very long 1D system, you could separate it in different parts where one could be a reservoir, one could be a piston, and it could be a second reservoir. And for example, you could shift the piston, make a tunnel barrier, and couple these two systems. You can then decouple the piston, you compress it, you couple it to a different reservoir, and thereby you could maybe make a heat pump from get excitation from one system to the other. And so you can go back. And of course, you can do that on the way of looking at it in a simple, classical thermodynamic types of processes. But you'd also think about it that these are basically quantum fields, and there's entanglement that is created by J. There is entanglement that can be, created by these couplings, and there's many of these type of things we can look around, and so the basic ideas are written down in this beautiful book about quantum thermodynamics, which was edited by Pinder, Gogolin, Anders, Adesso, and Correa something 2 years ago. And then there's an extended and really long 40-50 page paper, which was part of the PhD thesis of Marek Kulza from Jens Eisert's lab, who looked into really the theory and how to describe this type of system. So if you want to know everything you want to know about this system is written in this very long paper. Now, why is it interesting for quantum mechanics? First of all, I had shown you, due to the recurrences, we can make the system non-Markovian. And depending on, so to speak, depending on when you couple and decouple, the system has either completely forgotten its initial state, which is when it's in a classical statistical ensemble, or completely remembers its initial state. That's when the recurrence occurs. Depending on the tunnel coupling, we have the chance of doing weak coupling or strong coupling, and look at that, see how this happens of the system. Thirdly, when I couple and decouple two quantum systems, I introduce quantum noise again. Yeah, and this quantum noise which change the properties of the machines. Of course, in the thermodynamic limit, this quantum noise doesn't really play a role because it contributes a negligible amount of energy. But in a finite quantum system, this might be an important part, especially as you see that in experiments where it's very easy to see this quantum noise of in the fields. Then the coupling allows you to make entanglement, and with the optimum control of splitting and decoupling, we can create significant entanglement between the two parts. then we can use either a very simple lattice liquid as a medium, or we can use an extremely strongly correlated Gordon model. Yeah. And we can basically choose about all these things. And we can make many of these machines in parallel. And when you make them in parallel, you can suppress, the common properties, which would be classical aspects of the machine, and enhance the aspects that come from the quantum noise, because they will be different in each of these machines. So I think there's lots of fun stuff to be done by building this type of quantum machines. And I know, of course, we're working on it, and we can basically manipulate, make arbitrary potentials, split them, imprint excitations, and do whatever we want on this type of systems. And we can do local measurements, and you see that, for example, this is a non-translation invariant second-order correlation functions measured in a quantum fluid, and you see we have something like 5 orders of five e-folds that we can use for sensitivity in a correlation function. And if we introduce that splitting, you see that the two things get completely decorrelated for the moment, and if there will be some entanglement left over, we can look at it. So there's many of the things to be done, and there's many of the techniques to be developed, for using it, but playing around with it. So what we try to do in the next few things, we try to verify the operational primitives for some quantum field thermal machines, which is like compression, decompression, moving, splitting, coupling, recoupling. We have to develop the methods of local measurements of temperature, energy density, correlation, heat flow. And I think one of the first things you want to look is really study heat flow. So it's basically study heat flow that's given by the excitations, not study transport by the atoms, but transport by the excitations. And if we can do that, I think then the real fun starts of building interesting machines and looking at the role of information in quantum physics beyond what we now know about quantum information. So that gives me to the end. I think what have we learned from these type of experiments? I think these atom chips and these devices provide an extremely versatile platform for quantum experiments. We've shown that these atoms are exquisite local magnetic field sensors. And the interaction of the atoms leads to very interesting nonlinear physics. And it results in intriguing non-equilibrium dynamics, which on one sense makes it hard to do experiments with. On the other hand, gives you a beautiful, interesting physics. This many-body quantum system relaxes and decoheres even when it's completely isolated. So if you don't be careful, then you basically end up with a statistical ensemble. And underneath all this decoherence, underneath this emergence of the classical statistical ensemble in a completely isolated quantum physics, which you can say is that that's an emergence of a classical world in a quantum system without an observer. Yeah, is fully alive. Quantum system is fully alive, which can be demonstrated by these quantum recurrences. And I think what's interesting for atomtronics is the physics is described by these effective quantum field theories, and they control and experiment of the excitations in this quantum. And it's really, what would be really, goal is really to control and experiment with these excitations and do the physics with these excitations. And one prospect would be just building, quantum thermal machines with that. And yes, so that leaves me to an end. And there's a whole bunch of people that worked on this over the last years. And things that I showed was, Tariq Baradar did the optimum control of squeezing in the squeezing experiment. Bernhard Rauer, Thomas Schweigler did many of and Tim Lange did many of these experiments on the relaxation. Thomas Schweigler, on all these correlation functions. Yao Sabino is basically doing the experiments on the quantum thermodynamics. And there are many other things that we do on atomtronics devices, which I didn't really have time to talk about. And of course, there's lots of theory collaborations, with Igor Matsets now, here in Vienna, or Uli Hoynast on the optimum control. And of course, there's, Eugene Demler, Jürgen Berges, Tommaso Qualaco, and Jens Eisert, which are basically, my buddies we talk, and my students talk to nearly weekly. on the problems and help us understand the problems that, on our experimental data. And of course, there's over the years, many funding went into that. And yes, so thank you for listening.
Thank you. Immediately, there's one question from Luigi. So Luigi, do you want to ask a question?
Yes, I think it's thanks for this beautiful talk. So very, 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 very impressive. So I have a couple of questions. I have many questions, but let me ask one on dynamics on the 1D. Okay.
Yeah.
So you saw this thermalization of this of the 1D system, right? And I mean, you find kind of pre-thermalization, then generalize Gibbs ensemble, which is a characteristic of integrable theories, right? So I think one of the holy grail, let me say, in the field is to understand the so-called KEM theorem. So this Kolmogorov-Arnold-Moser theorem in the quantum regime, right? So,
yeah.
And say would be, say, the question is the following, say in simple terms. Say, you start for an integrable theory, and then you have a kind of thermalization, which is generalized Gibbs ensemble. So how about the perturbation of the integrable theory? Is still close to a generalized Gibbs ensemble or not? Okay.
So that's a very interesting question, and it's something.
No, so your experiment. So I presume you are not exactly in the integrable point, right? So you have, of course, you are not exactly in the Lieb-Lineker model, right?
No, none of these experiments will be exactly integrable. Yeah. And it has to do with that the Lieb-Lineker model basically, and then Maxime knows this much better. But in our system, there's always, the confinement gives always an admixture of higher modes, even though, there's a beautiful paper by Igor who showed that you can use virtual 3-body collisions to break integrability. Yeah, even in a perfectly 1D system. Now, the question is that, the KM theory would say, when does it really start to, when do you really start to see this integrability breaking? I mean, we did an experiment together with our friends in Beijing, which was some kind of a quantum Newton's Cradle experiment, where we had an extremely small admixture that breaks integrability. And we could observe these quantum Newton's Cradle oscillations over hundreds of oscillations. And it relaxes.
Mm-hmm.
Yeah? My goal would have been to see these 3-body,
excuse me,
yeah?
You are talking about Ulam-Pasta, the Fermi Ulam-Pasta oscillator. So it's a harmonic oscillator. Right?
No, it was an harmonic oscillator. But an harmonic oscillator in 1D plus some very small admixture of transverse excited states. And that breaks integrability, and that leads to thermalization.
Okay.
And it was very, very small. Yeah. Now, does it tell you something about CAM? I'm not we should, probably Maxime is a much better person to talk to, or would have to see, my thing is the following, is that, integrable systems are thought about as something exotic. And I don't think they are not exotic at all. The system what I showed you as a relaxation process of an isolated quantum system, I think is very, very general for any system that has long-lived excitations. Because in the time scale that is shorter than the lifetime of this excitation, the system looks like an integrable system. So any system which has not overdamped excitations has some aspects of integrability in its non-equilibrium evolution. Now, how does that relate to the CAM? I'm
no,
I'm an hardcore experimentalist, or
it's a very, very good question. So I think it's in a project with with colleagues in Boston, I think I'm studying this breaking of integrability, controlling and trying to understand dynamics. It's a mess. So it depends on for different models, you have a kind of you have a kind of dynamics. Then you cannot wait longer because you have problems also in understanding non-integrable dynamics a long time. So it's a very complicated problem. But I think it's I think your experiment say that you perturbation of an integrable system is still similar to an integrable system. So I at least this is what I understand.
Yeah. So there's some time scale which looks like integrable, and the characteristic of these prethermalized states is that that there is there's some kind of conserved quantities or approximately conserved quantities which lead to this prethermalized state and the GGE. Now, for some theories we know them. For others, we don't know them. When we find them, that there is these prethermalized plateaus. And I think all of them, and in fact, everything we looked at together with our quantum field theory friends, and Jürgen Berges is one of the guys who really invented this prethermalization, and from his numerical studies of quantum field theories, and in the end, you always find some kind of hidden conserved quantities which determine that. Yeah, if it now be in Floquet or whatever, I think you will always find them, and that's a very, very general way of doing it. And it was nice in our system. We could point our finger to what is it. It's the occupation numbers of these excitations that are close to conserved and which lead to the GGE and which lead to the other things, which lead to the prethermalized state. Yeah, but I think that's a very, very general principle of relaxation.
So I have a second question, but first might be Maxime.
Now, I want to just quickly comment on that. So as for KM in many body systems, I mean, we should talk again in 50 years, because the question is not resolved for classical systems.
Yeah.
So it is not clear if there is a KM transition. So for example, the one-dimensional classical field theory FIFO model is proven numerically, analytically, not to have a KM transition at all. I mean, it starts thermalizing as soon as you add this a small non-integral perturbation. So there's a gulf between few body, which is our solar system, and it's resolved. I mean, it's stable. There is a KM transition. We're still alive, but and many body systems. And another thing I want to say that I like Jörg's idea that at low excitation energies, I mean, all the quantum field theories are linearizable. So you have at least the occupation numbers of the elementary excitations you have as your pre-thermalized integrals of motion. Yeah. So
simply to comment that actually, so as you know, Maxime, I don't agree totally with you, but I think never doubt on a shortcut. I think this is
again, talk again in 50 years.
An important lesson, right? Okay.
That would be in heaven.
So if there are no
by Luigi, there is a question in the Q&A. So let me ask Roberta Citro to unmute herself and ask the question. Although Jörg, you can also read it directly from the Q&A.
Yeah, I'm trying to get to there where I can read all the things that just.
But Roberta, you can unmute yourself because asking the question.
Okay, now I can do that. Hi, Jörg. I'm interested to know if you can perform adiabatic quantum control of tunneling in your system in such a way that the system remains in the ground state.
If you do, yes. I mean, that basically would mean that you create a cat state. Or that you can create a state that has n-half and n-half, and maximum, squeeze state. In principle, yes. We tried to find out a way how to do that, but I think it's going to be extremely hard.
Yeah.
Maybe we can do it for, you can do it for two particles in a Hubbard model, in a Hubbard dimer. Yeah.
Yeah.
But if we can do it for 1,000 particles, I doubt it, because it's just too difficult. Yeah. We tried with MCDHX to see if we can do that for 100, and the conditions were, atrocious. And I think it's not clear for me. It was not clear if it was limited by the numerical accuracy of the model, or if it's, or by the, So I think it's going to be very, very difficult to do that. You might have a chance of doing it with optimum control much better than with adiabatic splitting. Yeah. Because you can do that much faster, but it's going to be tough. I think it's going to be very hard. I mean, we managed to do, in the calculations, we managed to get the factor of 100 reduction in the noise. Yeah.
Yes.
Yeah. But that basically means that for small systems, it should be possible. For large systems, it's not. And it was basically on an in a numerical model, which is much easier to do than in the experiment, where
Sure.
somebody walks by and and the apparatus shakes, and the things even though our experiments run run 24/7 and have a few percent variations if it runs well and things like this. And some of the data I showed you had tens to hundreds of thousands of experiments to do the statistical, to look at the statistical ensembles. Yeah, which is the advantage. That I think you can only do that because of integrated devices. Otherwise, it would be extremely difficult.
Yeah, sure.
Yeah. But looking at the squeezing and doing that is one of our goals in the future, to look at that. But I doubt that we can really go into a perfect. Right.
Yeah, because I mean, all this Lattinger liquid picture, of course, can break down if you don't do that adiabatically, for example, no? Because if you want to couple two Lattinger liquids, for example, and so you switch on tunneling, but if you don't do that properly and adiabatically, then the Lattinger liquid picture completely breaks down.
There's also another one from Professor Hunter. Carsten, you want to say something?
Yeah. Okay, so Jörg, thanks for these beautiful results and your deep thoughts. So my question is, can you wrap me up about the mechanism for the finite lifetime of these elementary excitations? So you mentioned this three-body virtual something, but
now you get to a very sore point. We did a whole series of experiments in the linear response regime. So basically, where you write, an average, a single excitation in the system, and then measure its propagation and, measure, making shock waves not with 50% or 90% amplitude, but with a few percent amplitude, which means that there's, really very few quantum of the excitations in there, and wanted to measure their lifetimes and things like that. And it turns out that the experiments were, number one, the lifetimes were short, and it was shockingly short. And second of all, experiments were not consistent. So either, even though we have this enormous control about all of the parameters, somehow we didn't manage to get an. And of course, we wanted to write a single mode in there and look at pair creation of modes and all these other things, yeah, and look at the lifetime and see that free body and everything, yeah, and it didn't work out. Now, what we did in the end is that we wrote the modes directly in there in the density quadrature, and then the systems became extremely robust, and the experiments became robust. And we lately used, this generalized hydrodynamics, which is a beautiful, by the way, I think it's something that's much better than GPE to calculate this type of systems. And it's much more robust and much simpler to use. And we did an extension of GHD in the last year, also in the dimensional crossover regime, because GHD usually is for perfectly integrable system. And that looks to be, describe everything we see without any free parameters, and we're basically writing it up. Yeah, but Now, this is a numerical tool that doesn't give me any insight why the numbers are like that. Yeah. And so if you would have asked me 3 years ago or 4 years ago when we started this type of experiments, I would have said, all these excitations live much longer than in 2D or in 3D. Yeah. And it's not true.
So when you say short, is that short compared to, let's say, this axial oscillation period, or?
No. I mean, they're not overdamped. They're not overdamped. Yeah. So there are, you see a few of these oscillations, but you don't see hundreds of these oscillations.
Okay.
Yeah. Which I would have expected. If you would have asked me, years ago, I would have said, you're going to see hundreds of excitations. I was, looking at, hey, this is cool. We can make this excitation, this spectrum and something, and we measure that. And, it's a sore point, it's a very sore point. And I don't, experiments are tough. We just have to understand what's going on. Yeah. And I don't want to write a paper where I just, show a few pictures and say, hey, I don't understand. Yeah. But, yes, I would love to know why. And if there's some theoretical insight, yeah, please call me up,
Okay, I'll let you know.
Yeah, but it's crazy, it's crazy. And but it comes out in GHD, it comes out to be correct with generalized hydrodynamics. Yeah. And also across the crossover regime. Yeah, that's what I can say, but that's experiments from the last few months. Yeah, but it was also a much more gentle way. It was maybe it has to do something with producing short waves if you make excitation. So what they wanted to do first, we did then a parametric oscillator like you do a dynamical Casimir. Oscillate the walls on the side with a certain frequency and make an excitation. Yeah, and that didn't give a stable result. If we did the experiment by writing in the density quadrature of the excitations and then looked at the physics and the parts, it was much more robust and simple to do. And with a digital mirror device, you can do that. You can write any excitation in there you want and look at the time evolution of it. And you can also write them in there with extremely strong amplitudes, like 90% of the density, or write them in there with only 1 or 2% of the density and see, either linear response or the nonlinear physics. And GHD describes everything in one.
Yeah, you have a few more minutes before you head home. But Luigi has a question. So
yes, I have a second question if I'm allowed. So
yes,
this is concerning the correlation functions that you computed, so you measured in your experiment for the Cyborg model. Okay, so the question is on entanglement. So the way in which you measure entanglement is through the so-called reduced density matrix, and the matrix elements of the reduced density matrix are correlation functions. So of course, if you have then two-body correlation functions, you can understand simply the two-body entanglement, right? But if you have higher body correlation functions, then you can access say the entanglement between different blocks, let me say, right? So say in principle, if you have all correlation functions, you have the reduced density matrix, then you have access to entanglement. You don't have all the possible correlation functions, but you have many, right? So so people try to understand so how quantify entanglement if you do not have access to all correlation functions. Jens Eisert knows these things very well.
Yeah.
Right. Also, say in principle, then you can make a very good estimate, because I saw correlation functions of 10 bodies. Am I correct? So
yeah,
very large ones. So in principle, you can then reconstruct all density matrix using these blocks, and then you have access to entanglement.
Yes, it's not that simple because what we measure is one quadrature component of the excitation. Yeah, we measure the phase quadrature.
Only,
And
only,
we look
only-
at, we only
Okay.
measure one quadrature component, and we have to reconstruct the other one.
Okay.
Yeah. So it's not that straightforward. And we have developed with Jens over the years a tomography technique, a many-body tomography technique to reconstruct
Yes.
both of them.
Yes.
And we're working on extracting, area loss and volume loss and things like this out of the system.
Yes.
Yes. Yeah. But it's not as, yes, it would have been, beautiful to do that right
Yeah,
away with things, but it's not. We only have a single, we have only one quadrature component available. Yeah.
And only small remark. So I think you work with Daimler. Then I mean you know very well. I think Eugen went to a proposal in which he comes from. You want to measure the entanglement entropy. You go from 1D system, you split in two, and you reconnect. You clone, split in two. I think you have the technology to make this this Daimler setup, right?
Yeah. We're talking to him on this, yeah.
Yeah.
But it takes time, this experiments always take time.